Welcome to our fifth lesson on geometrical optics. We'll be discussing Snell's law today. Now let us just quickly recap again what happens during refraction. Remember, refraction was the bending of light. So when light hit, this case, a glass block at an angle, it will bend. Now we always need to go and draw a normal line which is 90 degrees where that light actually hits the object, and we sometimes refer to the object as the obstruction. So 90 degrees to that, we'll go and draw in a normal line. Now if your light ray goes from a less dense medium to a more dense medium, we said in our previous lesson, then the light ray will bend towards the normal. That means it's not going to continue traveling straight through, it will bend slightly more towards the normal. Now when you go and look at your incident angle and your refracted angle, your incident angle is always between the incident ray and the normal. And if you go and look at your refracted angle, the first angle of refraction is then where you have your refracted ray and the normal. Now note though that this incident angle is not equal to the refracted angle, as you can see, and that is due to the density difference of the medium. As we said, it will not continue traveling straight through the light ray, it will in fact bend, and because of the bending, obviously you end it with a smaller angle. Now they've tried previously to go and determine a relationship between this incident angle and refracted angle, and therefore decided to go and draw a graph with these values. So on my y-axis they decided to go and draw the angle theta of incidence and then the angle of refraction. Now note that this is obviously measured in degrees, each one of them, and when they did draw the line, they realized that they did not even find a straight line, but they found a line that curved upwards. Now from this line they could not deduce any relationships. Remember, as we said previously, when we looked at your force, acceleration and mass relationships, we do need straight lines through the origins of the graph, meaning the starting point here where x and y intercepts, in order to deduce relationship. This skew line is obviously not a straight line, and from this we cannot go and conclude a relationship. Now Snell decided to go and do it slightly different. He was a physician that worked on geometrical optics. So he decided, instead of just using the angle's value, to go and use sine of this angle's value. So we'll use sine of the incident angle on my y-axis, and on my x-axis sine of the refracted angle. And from this he went and found a straight line. So he was able to get a straight line through the origin of the graph, which basically means that our sine theta of incidence is directly proportional to the sine theta of the refracted angle. And that means if, for example, my sine theta of my incident angle is double, then my sine theta of my refracted angle will also double. So as the one goes up, the other one will also go up. So as said, the moment that you've got a straight line going through the origin of the graph, then we can deduce a relationship. And in this case it means a directly proportional relationship. So Snell's law refers to the relationship between the angle of incidence, the angle of refraction, and the refractive index when light moves from one medium to another. So therefore we can deduce from Snell's law and the relationships the following formula. Now refractive index, just to remind you again, refers to light, specifically the speed of light in air, the change of that as a ratio towards the speed of light in the new medium. Now your N here indicates your refractive index initially of your first incident ray. The sine theta is then the sine of the incident angle. The next N stands once again for the refractive index, but now of your second optical medium, and sine of this refractive angle. Now either three of any of these variables can be given for you to go and calculate the fourth variable. Now we're going to quickly look again at the relationships between the angle of incidence, the angle of refraction, as well as the refractive indexes. And then from that we will be able to deduce a few properties of Snell's law. So once again, our angle of incidence is between the incident ray and the normal, and we said that is not equal to the angle of refraction, which is between the refracted ray and the normal. Now, the first object is then our optical medium 1, which means in Ayres' case, this refractive index is usually a constant of 1. And then obviously depending on what the next object is, the refractive index of that specific medium, which will either be given to you or you will be able to go and calculate, is then known as the refractive index of that specific object. Now the first property that we can basically go and deduce is that if this angle of refraction for the optical medium 1 is very close to the angle of, sorry, say that again. If the refractive index of the optical medium 1 is very close to the refractive index of the optical medium 2, then we will have also an incident angle being pretty much just as big as the refractive angle, because our refractive index indicates to us how much bending would occur. So if the two values of the mediums are pretty close, then it means to us that there's not much refraction that will occur. Therefore, your incident angle would be very close to your refracted angle. So therefore, if the optical density of these mediums do not differ too much, then the refraction would not be as obvious. Now, if your refractive index for the first optical medium is far greater than that of the second medium, then your angle of incidence will be smaller than the angle of refraction. So that basically means if my refractive index is bigger than the second medium's, if the refractive index of the optical medium 1 is greater than that of the second medium, then it basically means that we're going from a more dense to a less dense area. And then my light ray would bend away from the normal. That is how come our angle of incidence over here is going to be far smaller than our angle of refraction on the other side. And the opposite will also be true. So if my refractive index of the first medium is smaller than the refractive index of the second medium, then my angle of incidence will be greater than my angle of refraction. And a typical example of that is when I go from a less dense to a more dense medium. Therefore, my light ray will get refracted more towards the normal. Therefore, the angle of incidence is greater than the angle of refraction. Now, the question which I would like you to go and attempt is where, according to Snell's law, how would the angle of refraction compare to the angle of incidence if the refractive index of medium 1 is more than in medium 2? Remember to first pause your play and attempt the question before you'll be looking at the answer. The question basically asks is how our angle of refraction will compare to our angle of incidence if the refractive index of my first optical medium is greater than of the refractive index of my second optical medium. Now, if we have this scenario, it basically means for us that we will start off here with a more dense medium and end up going to a less dense medium. And then my light ray will bend towards the normal. Oh, no, I'm lying. Then my light ray will bend away from the normal. And if it bends away, then it means my angle of refraction is then greater than my angle of incidence. So you can also remember now, the angle of incidence is thus smaller than our angle of refraction when we look at going from a more dense to a less dense medium. Now in our next lesson we'll be looking at calculations using Snell's law.